Okay, this is a exam debrief on what you did for the semester exam. We had 28 questions on section 1, part A, had 55 minutes to go through it. I'm going to break this video up into a number of different segments, each one about 15 minutes long. You should know how to do all the problems on this test. Most of these questions were taken off of previously released BC exams. Okay, so first one, integrate the cosine, our basic integral rule. Integral of cosine of u du is sine of u. In this problem, the u is 3x, so the du is 3dx. We don't have 3dx, but we can easily get a 3dx, just put a 3 in there. 1/3 would compensate, so we have 1/3 sine of 3x, and don't forget to add the constant. 1/3 sine of 3x. Choice C is the answer. Number 2, this is a limit problem actually from pre-calculus. If you notice that direct substitution gives you 0 over 0, which is not the answer. There is an algebraic technique that says you look at the highest power of x and you divide through by that. So we would be considering this expression here where we have 2x to the 5th divided by x to the 5th. We're just dividing through by the highest power, plus 6x squared divided by x to the 5th, and all that's over 4x to the 4th divided by x to the 5th. You might remember this from last year, 3x squared over x to the 5th. And then we simplify each of those, so we have the limit, x goes to 0. Here, the x to the 5th cancel, so we just get 2. Here, the x squares cancel, so we get 6 over x cubed. Here, the x to the 5th, or x to the 4th cancel, so we get 4 over x. And here we get the x squares cancel, so we get 3 over x cubed. And then the question is, what happens to this as x gets really, really tiny? So x is going to 0, says that x is getting tiny. Now this thing is just going to blow up, right? That's going to get really large as x gets tiny. Whenever you divide by a tiny number, the quotient gets large. And likewise, all of these things get really, really large. So we have sort of like infinity over infinity. And the question is, what do we do with that? You know, does that give us an answer? I did show you L'Hopital's rule. L'Hopital's rule may be able to give us a clue as to what's going on here. L'Hopital says that whenever you have infinity over infinity, you can approach this by derivatives. So we don't need the algebra approach, even though that's a useful start. Rather, let's look at this limit instead. Limit x goes to 0. We take the derivative of the top, which is 10x to the 4th plus 12x, and the derivative of the bottom. We are not using the quotient rule here. 16x cubed plus 12 plus 6x. Do my multiplication right here. And again, we note that as x goes to 0, this is still 0 over 0. So we'll, again, use L'Hopital's rule here and look at the derivatives once again. X is going to 0. So we get 40x cubed, right? 40x cubed plus 12. And here we get, what's that, 48x squared plus 6. X is going to 0, so we can substitute x is 0 in here, and we get 12 over 6, which is 2. So 2 is the answer. 2 is the answer to this problem. Okay, number 3. This is a question about continuity. There's something going on at 3. Notice we have a parabola for values less than 3. And if we had a little sketch going on here, here's 3. There's some sort of parabolic behavior over here, and then a linear behavior for numbers bigger than 3. And the question is, what happens at 3? We want this actually to be continuous, however it hooks up. And to make that happen, we have to consider the left and right hand limits as x approaches 3 from the left and from the right. So let's look at those. Limit as x approaches 3 from the left, we're using this rule, x squared minus 3x plus 9. We're putting 3 in there, so we get 9, take away 9, plus 9 is 9. And now we also have to consider what happens when x approaches 3 from the right. Now we're using this rule, k x plus 6, so we put 3 in for x, and we get 3k plus 6, and these two have to be equal. The left-hand limit and the right-hand limit have to be the same for the limit to exist, for the function to be continuous. So that's not terribly hard. 9 is the same as 3k plus 6. 3 is 3k, k is 1. So that's the answer to that problem. Number 4. We're just doing a derivative. This looks like a simple chain rule problem. It's probably easier to write the problem as the sine of 4x cubed to more clearly see the 3 links in the chain. So the first link is this cubic. So we have 3 times the sine of 4x squared. And then we have the sine function. The derivative of the sine function is the cosine function. The angle stays the same. And then we have the 4x function, and the derivative of 4x is 4. So cleaning these up, 3 times 4 is 12. We have sine squared again, and then we have cosine. So 12 sine squared cosine. There we are. Okay, so we have this integral function. Notice that f is defined as an integral, and then you're looking for f prime. So fundamental theorem of calculus, part 2, says if we're finding the derivative of an integral function, a to x of some function t, it's simply f of x. So we can find the derivative of this integral function very quickly. F prime of x is simply going to be the cosine of 3x. But now we need to evaluate that at pi by 6. Pi by 6, so that's the cosine of 3 times pi by 6, which is the cosine of pi over 2, right? And quick unit circle, pi over 2 is the top of the circle, and the coordinates there are 0, 1. The cosine of pi over 2 is 0. Okay. Number 6. Let f be the function given by which of the following is an equation. For the line tangent to the graph, we have a point where x is 1. This screams the point slope form of a line, m times x minus x1. We know x is 1. We could easily find y. So we'll just put 1 in here, and we get, what, negative 1 cubed times 1 plus 1 is 2. That's negative 2. And that's going to fit in here. So right now we have y plus 2 m times x minus 1. Well, that didn't help us at all because they all say that, right? Y plus 2 and x. So what we need now is the slope. That's sort of the key on this problem. How do we get the slope of the tangent line? And that is the derivative. So f prime of x. We're going to use the product rule here. So the derivative of a product, I don't know how you remembered it. Some textbooks say to just write down the first function, which is 2x minus 3 cubed, times the derivative of the second, and then plus the second, which is x plus 1, times the derivative of the first. And this is where it gets a little tricky. it's 3 times 2x minus 3 squared, but then times 2 because of the chain rule, right? So we're trying to clean this up a little bit. In fact, we need the derivative evaluated where x is equal to 1. So f prime of 1. So what would that be? That's negative 1 cubed times 1 plus 2 times 3 times, all these are multiplied together. We're putting 1 in, so that's negative 1 squared times 2. So what do we have? Negative 1 plus, so this is 6 times 1 is 6, 12, which is 11. Choice D is the answer. Tricky problem. If you had remembered the derivative of a product slightly differently, some students do that, where they say the derivative of product is the derivative of the first. Again, you would have to start off with the 2x minus 3 squared times 2, derivative of the first times the second, plus the first, times the derivative of the second. You'd still get the same answer when you substitute 1 in. You would get 11. Okay. Number 7. This is an integral function. There's obviously e to some power. Let's see our integral rule. The integral of e to the u du is simply e to the u. In this case, we have e to the square root of x, sort of in the integrand right here. So it makes sense to say u is root x, which means du is 1 over 2 root x dx. And if we look at the problem the way it's stated, we've got the, maybe if I rewrote it slightly different, it would be a little bit clearer what's going on here. We have the integral of e to the root x, and then we have times 1 over root x dx. And of course, what we're missing is the factor of 2. Okay, so that's the way the problem's stated. We need this 2 here. So we'll go ahead and put that in the denominator and balance it with the 2 in the numerator. So now we have, just looking at the structure, we have the integral of e to the u, and we have du. So the answer is going to be 2e to the root x plus your constant. 2e to the root x plus your constant, choice A. Number 8. Here's some crazy function. The figure above shows a portion of the graph. Which of the following could be values of constants A and B? So we notice a couple of things. First of all, in the end, in behavior, this is y is equal to 3. So the limit as x gets really large of this function is in fact 3. And we know that occurs when the ratio of the leading coefficients, now again, look at the coefficients we have, a over 1. A over 1 has got to be 3. So A could be 3, right? That's a nice option. When we look down, we do have a couple choices where A is 3. We also have a vertical asymptote here at x is 2. And that occurs when the rational expression has an x plus 2 in the denominator. So we know we need to have, an x minus 2 in the denominator because this is x is equal to 2. So how can we get an x minus 2 given the x squared plus b? You go, well, let's think about it for a little bit. If b were negative 4, so if this were x squared minus 4, then it would factor as x plus 2, x minus 2, and we would have the correct expression in the denominator, x plus 2, x minus 2. Okay, so it looks like b has got to be negative 4, and in fact that is the correct answer. And so a is 3, b is negative 4. As an aside, because we know that we're going to have both of those factors in the denominator, this is in fact only a portion of the graph. We could surmise pretty clearly that if we had going out here to negative 2, there would be another vertical asymptote here, and the graph would look something like this. So it would come up and then go back down. And then because this is x is -2, this is an odd pole. Here's our end behavior. We know the graph has got to go like that. So yeah, the entire picture would look like that. We only had part of it, which is okay. That's sort of a pre-calculus type of problem, by the way. R and H are considered constant. What is this integral? How does it clean up? Okay, so it's a definite integral. We're going to have to find an antiderivative and then plug in H and 0. So let's look at the integral 0 to H. We have a pi. I'm going to go ahead and square this expression just to get it out of the parentheses. Okay, so that's the problem that we have. But then we're told that R and H are both constants. We know pi is a constant, and we can pull these constants out in front. So pi R squared over H squared. So the only thing we're really integrating is the x squared dx. And that integrates pretty simply. So here's our constants, pi R squared, H squared. The integral of x squared is x cubed over 3, and we're evaluating that between 0 and H. So fundamental theorem part 1, here's our constants again, pi R squared, H squared. And then fundamental theorem says we take the antiderivative, we substitute in the upper bound first, so that would be H cubed over 3, and then the lower bound second, which would be 0 cubed over 3. And now we just have to clean this up. Okay, so not terribly impossible. What do we have? We have, let's see if I can, here we are. So we have pi R squared H cubed H squared times 3. This is obviously just 0. So the H's cancel, and we have pi. There's a 3 in the bottom, and we have R squared H. And that's the answer we're looking for, pi over 3, R squared H, pi over 3, R squared H, choice B. Okay. Number 10, velocity is the derivative of position by the fundamental theorem. Again, we're seeing this, the integral from a to b of f prime is in fact f of b minus f of a. Or by rearranging, if we move this f of a to the left side of the equation, we have f of a plus the integral of f prime of x between a and b gives us f of b. And by the way, when I took this off of a released exam, this was the problem that was on the test. I had just sort of added this as a, by the way, you're supposed to know this. This would not be given to you in May. You're supposed to know that up front. Particle moves along the x-axis so that any positive time, velocity is given by this. This, in fact, is the derivative of position, right? So velocity is, in fact, the derivative of position. We know that. And if you want to think of it as x prime, we can do it that way. X prime of t. Velocity is the derivative. Particles at position 7 at time is equal to 1. So x of 1 is 7. What is the position at t is equal to 2? We need x of 2. That's what we're trying to find. And we know velocity is the derivative. Okay, so we're just going to use this form of the fundamental theorem right there. We're going to take the initial value. Let me do it in terms of x. X of 1 plus the integral from 1 to 2 of x prime of t dt will give us x of 2. Right? And if you just sort of look at this and see how it matches up very, very nicely with this expression right here, then this should be relatively straightforward. Let's put in the stuff that we know. We know x of 1, that's 7. we're going to have to figure out the integral from 1 to 2 of the derivative, which we were told is 4 minus 6t squared dt, and that will give us x up to. That will give us the position at time t. So the crux of the problem is just find the antiderivative and plug in the numbers 2 and 1, which isn't terribly hard. Okay, so the antiderivative is going to be 4t minus 6t cubed over 3, right? And we're going to evaluate that between 1 and 2. Okay, so we'll put the upper bound in first. So 4 times 2 is 8. This cleans up to what? Just 2t cubed. Let me write it that way to make it a little bit easier to see. 2t cubed. And we're putting the upper bound in. So 2 cubed is 8 times 2 is 16. And then we got to put in the lower bound. We put 1 in and we get 4. And we put 1 into there and we get minus 2. Okay, so a little bit of arithmetic. No calculator here, but these numbers are pretty easy. 7 plus minus 8 minus 2, right? So 7 plus a negative 10, which is negative 3. Okay, so we find that choice, which is right there. Choice C. Okay, number 11. This looks like a straightforward derivative problem. Sure, chain rule again. We should know the derivative of the cosine of u is minus sine of u. And be sure to use the chain rule. So the derivative of a cosine of minus 3x is minus the sine of minus 3x, and then multiply that times the derivative of the inside, which is negative 3. So cleaning that up, we have what? 3 sine of minus 3x. Okay, so 3 sine. None of these have a minus 3x. So even though this is the right answer, it's not one of the choices given. Shucks, we've done the calculus correctly, but now we need to remember something about trig. If we look at a sine wave, we note that this is an odd function. And if we go out to any value theta, and we find the sine of theta is that height, and then we go to the opposite of theta, and we find the sine of the opposite of theta, it's the opposite of the sine of theta, right? That's the definition of an odd function. The sine of minus theta is the opposite of the sine of theta. So this minus 3x, and that, I guess you needed to know this to get the right answer. That is the same as minus the sine of 3x. Okay, so our answer here is going to be minus 3. I made this look like a fraction bar. This is not a fraction bar. Let me just do it this way. Equals 3 times minus sine of 3x. So answer is minus 3 sine of 3x. Choice A. Calculus wasn't hard. The trig, you had to remember odd functions. Number 12. By definition, the derivative f prime of c gives the slope of the tangent line to the graph of f at the point where x is c. What's the slope of the tangent line? And again, I think when I saw this on the released exam, this was the question. They didn't tell you this previous part. You're supposed to know that. And I sort of threw it in just to help remind you how to do this type of problem. What we're looking for, when you see the prompt, what is the slope of the tangent line, you need the derivative. So y prime. Here's y. This is a quotient, so we're going to use the quotient rule. The derivative quotient is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. 1 minus x quantity squared. Cleaning that up a little bit, not that we have to. We've got what, e to the x minus x e to the x plus e to the x. There's 2 e to the x's up top, and on the bottom we just have 1 minus x quantity squared. We're supposed to evaluate this at x is equal to -1. So y prime of -1 is e to the -1 minus -1 e to the -1 plus e to the -1 all over -1 minus a -1 squared. So what do we have? This is e to the -1 plus e to the -1 plus another e to the -1. That looks like 3 of those up top and on the bottom. We've got 1 plus 1, which is 2, 2 squared, which is 4. So it looks like we have 3 e to the -1 over 4. Is that a choice? We're looking for 3 e to the -1 over 4. I don't see that explicitly, although we do know that when you have e to the -1, we can just throw that down in the denominator. So 3 over 4e. 3 over 4e. Choice B. Number 13. I'm going to stop this at 20. We'll stop this after this problem. And then that'll give us about a half an hour for the first half, and then we'll do another half an hour video for the other half. By definition, the derivative of the limit of a difference quotient is in fact the derivative of the function f at c, and your task is to evaluate this limit. On the AP test, they would not have told you this. You're supposed to know that. They simply say evaluate the limit. I gave it to you just to remind you of one way of working this problem. So if we just sort of match up the pieces, we see that c is equal to 1. C is in fact equal to 1. The function is e to the 3x. And this part, this f of c, would have to be e to the 3x evaluated at 1, which is in fact e to the 3. So everything matches up exactly the way it's supposed to. We've got the function, we're subtracting off, right, e to the 3, and we got 1 minus x, or x minus 1 on the bottom, and x is going to 1. So this is just the derivative. That's all this is. This limit is in fact the same as f prime of c. F happens to be e to the 3x. C happens to be 1. So here's the derivative, which is 3e to the 3x. And evaluated when x is equal to 1 gives us 3e cubed. 3e cubed. Choice D is the answer. You could have done this using L'Hopital's rule. We had talked about L'Hopital's rule a couple weeks ago. If we look at L'Hopital's rule, direct substitution, we try plugging 1 in, we get 0 over 0, which is not the answer. So we take the derivative of the top. The derivative of e to the 3x is 3e to the 3x. The derivative of this constant is 0. And the derivative of the bottom is 1. So now we'll work this problem. And direct substitution gives us 3e cubed. Either way. Okay, let me stop this one here, and then we'll pick this back up with problem